In 10.4, we're going to continue with our conversation about arcs and circles and angles and things like that. We're going to focus here on inscribed angles and intercepted arcs. So an inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of a circle. So an inscribed angle is basically what you see here in blue. Notice that the vertex is on the circle. So the vertex is on the circle, and notice that the sides of the angle have these chords within them, right? That form part of the sides of the angle. So that's what an inscribed angle is. An intercepted arc is basically the arc piece that is kind of trapped in between those two sides, angle sides. It's this piece right in here, right? It's this. It's the part of the circle that's sort of trapped, and so we call that the intercepted arc. So theorem 1010 talks about what is the measure of an inscribed angle, right? It's measure of an inscribed angle theorem, and it basically tells you that the measure of an inscribed angle is half the measure of the intercepted arc. So this angle here is going to be half of whatever the degree measure of the arc is, the intercepted arc. So, for example, if the intercepted arc is 100, then this angle is 50 degrees because it's half of the 100. If the intercepted arc is, 90, then this angle here, this inscribed angle is going to be, 50 is not half of 90, is it? No, it's not. Sorry, it's going to be 45 degrees. So it's always going to be half of the arc, and so you can also work that in the other direction. If you know that this angle, let's say, is 60 degrees, then you know that the arc is going to be double that, or 120 degrees. Okay, so if we're looking for the arc, we double 2 times the angle. If we're looking for the angle, it's half of the arc. So that's the relationship. The second theorem we're going to talk about in this section is, again, inscribed angles of a circle theorem. And it basically says if you have 2 inscribed angles of a circle, and those 2 inscribed angles intercept the same arc, then the 2 angles are congruent. And again, let's kind of think about that. It makes perfect sense. Here we have angle 1. This is inscribed angle 1. And notice that the intercepted arc is this green arc here. So we know if angle 1 is, let's say, 30 degrees, we know that this arc is 60 degrees. Makes sense, right? Well, notice here we have inscribed angle 2. And inscribed angle 2 also has this 60-degree arc, which means, again, angle 2 is going to be half of it, or 30 degrees. So what this is saying, we just proved it, is that if the 2 angles, the 2 inscribed angles, intercept, right, the same piece of arc, AB, then those 2 angles are going to be the same. They're both going to be half of whatever AB is, right? We keep going here. We're going to talk about some other inscribed shapes. So not just inscribed angles, we're going to talk about inscribed polygons or circumscribed, right? We're going to kind of learn what does that mean, right? So an inscribed polygon, definition for an inscribed polygon is a polygon with all of its vertices on a circle. So for example, when we're talking about the triangle, it's an inscribed triangle because it's inside the circle and all its vertices are on the circle. Same thing with the quadrilateral. If we're talking about the quadrilateral on the right, it is inscribed because it is inside the circle and all of its vertices are on the circle. Okay? Now, the circles, we call those circumscribed circles. And the reason we say that is because those are circles that contain the vertices of an inscribed polygon. So it's a special kind of circle just because it's around an inscribed shape and all the vertices of the shape are on the circle. So what can we use this knowledge about inscribed triangles and inscribed quadrilaterals and polygons? Well, we're going to use it first on an inscribed right triangle. So if you look here, this triangle in here is considered inscribed because notice that the triangle has three vertices, A, B, and C, and all of them are on the circle. So if you happen to have a right triangle that is inscribed in a circle, then the hypotenuse is the diameter of the circle. And that makes sense. Notice here, this is a right triangle, and notice that the diameter also is the hypotenuse. So again, it's a good thing to know. Now, conversely, let's just say that you know that one side of the triangle, let's say you didn't know that this triangle was a right triangle, but you knew that this side of the triangle was the hypotenuse. Well, then you could conclude that the triangle has to be a right triangle, and angle B would have to be the 90-degree angle. So again, you can either know this is 90, and therefore you can conclude that this is the hypotenuse, or you know this is the hypotenuse, or the diameter rather, right? Which means that you know that this is 90 degrees. So let's work some problems out, right? Well, actually, this one has one more theorem. I think this is the last theorem for this. And it basically talks about inscribed quadrilaterals. And in inscribed quadrilaterals, what you have, is, again, a four-sided figure. That's what a quadrilateral is. All the vertices, the four of them, are on the circle. So it's definitely an inscribed quadrilateral. And there's a theorem that applies to these angle measures. And it says that the opposite angles are supplementary. So the theorem, it's a biconditional statement really, and it says a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So if you're told that it is inscribed in a circle, then you know the opposite angles are supplementary. Or if you know the opposite angles are supplementary, you can conclude that it is inscribed. So that would mean that angle 1 plus angle 3 have to equal 180 degrees. And you know that angle 2 plus angle 4 also has to equal 180 degrees. So now let's try to, apply this, right? An angle inscribed in a semicircle is a right angle. Well, again, we know that because, again, look at this. We've got angle 1 here is formed by these two sides, right? So this is our inscribed angle. But notice that the side opposite it is the diameter. Well, when the opposite side is the diameter, we also know it's a hypotenuse. And we then know that angle 1 must be a right angle. So we already sort of knew this. So let's try to actually apply it now to some problems, right? So we're looking at this, and I know it's a little bit faint. It's a little hard to see, right? But angle Y refers to the whole thing, okay? That's what they're basically saying there. And this angle here is the 20-degree angle that they're referring to. So notice the center is at 0. We've got all these kind of weird shapes. So we really got to think about what we know, what we have, what we don't have. So let's think about this 110-degree arc that they gave us here. They said this piece was 110 degrees. Well, let's see if we can figure out what inscribed angle it goes with. Notice that that intercepted arc is created by this angle. And I know then that this angle has to be half of the 110. So I know this piece here is 55 degrees. So that's already a starting point. I'm able to find some angle. They're looking for X and Y, but I got to start somewhere, right? So the second thing I know that they told me is they showed me that this angle here was 20 degrees. Well, my inscribed angle here intercepts X, right? This arc right here. So I know that if the angle is 20, I know that this arc is going to be 40. So I know that X is going to equal 40. because again, it's going to be, that arc is double the other one. So now I'm like, okay, I'm starting to get, the hang of this here, right? What else could I do here, right? What other angles do I know? Maybe did I learn another theorem in this chapter that, in this section that would help me? And what I noticed was, remember that if two inscribed angles share the same arc, those inscribed angles are equal. Well, notice that this angle right here, this green angle that I'm creating, is also using arc X, right? So that means if arc X is 40, if this angle over here is 20, this one also has to be 20. And so now I know that it's kind of hard to read, right? But I know that angle Y, which is the whole thing, is going to be 55 plus 20, or 75. So Y is 75. And I was able, again, to find that using the different rules. So we've used inscribed angles here. We've used, when two intercepted angles share the same arc, or intercepted arc. So again, we've got a lot of things that we look at to kind of come up with these final answers and these numbers. Let's kind of do the same thing, and let's try to figure out B. So again, in B, we know that one thing that I see that jumps out at me is this side here is the diameter. And so I know if that side's the diameter, I know that this is a right triangle here. So angle Y, which is these two things, well, angle Y is 90 because it's a right triangle. So I already was able to do that just by knowing that the diameter is also the hypotenuse in this scenario. The second thing they told me is that this angle here is 20 degrees. Let me do a different color. This angle is 20 degrees. So if this angle is 20, I know that the arc that it intercepts is going to be 40. And I quickly noticed that angle X, that inscribed angle, also has the same arc piece. And so therefore X is going to be the same as the 20. It's going to be half of the 40, or 20. So X is 20 degrees. So again, using a couple of the strategies we learned in this chapter, or theorems, we know how to solve for these missing pieces. A couple more problems. And so again on here, I have to pretty much go piece by piece. Like I kind of have to create my angles here, right? And I realize, oh, if this angle is 60, this intercepted arc is 2 times 60, right? Which is 120 degrees. So I know that X is 120 degrees. Then I sort of erase what's here, and then I kind of go again to the next one, right? And I'm like, I'm looking for Y. So notice that Y, I already know that this arc from here to here is 140. That was given. I know that this green arc here, that I just kind of covered in black, that one's 120. Well, I know a whole circle has to add up to 360. So Y is going to be 360 minus whatever's already there, 120 plus 140. So together, 120 plus 140 are 260, which means that Y is the extra 100 that's left over. So 100 plus 140 plus 120 have to add up to 360, and they do. So in C, X is 120 and Y is 100. This one here is a little bit problematic because this is not supposed to have these like little, this is supposed to be a straight line. So even though it doesn't appear to be a straight line, this is supposed to be a diameter. Okay, so on yours you might want to fix it, and it goes through the center. And so with, now that you know it's a straight line, I think it'll be a little bit easier for you to solve. Again, we notice that the diameter and this chord right here create this inscribed angle and this intercepted arc. So this intercepted arc is 80, which means this inscribed angle is 40. So X is 40. We're good there. Then we've got to try to figure out, okay, what else do we know, right? What's the other piece? Well, we know if this is a diameter, we know that this is a 90-degree angle right here. And we know that if it's a 90-degree angle, the interior angles of a triangle, right, always add up to 180 degrees. So 40 and 90 is 130, and this would be another 50 degrees. So if that's 50 degrees, now I can kind of see that angle as inscribed, and this would be its intercepted arc, which makes sense because 50 plus 50, right, 50 times 2 is 100, and notice that this forms a half circle, and 80 plus 100 is 180. So that makes total sense, right? So now the other side, so now we're like, okay, well, what, for example, would we do? Well, remember that we learned a theorem a little bit back. We said that if two chords were congruent, then their arcs would also be congruent, which means then that this arc here has to have the same value as this one. So it's also 100. And lastly, we've got 100 and 100 and 80, so that's 280. So we know that this last piece is also going to be 80 degrees or whatever. And so that should help us figure out what y is, because if that's 80, right, then if the inscribed or intercepted arc is 80, the inscribed angle is 40. And so again, I can do a couple of things. I know this is 90, and then if that's 90 and 40 is 130, I know y has to be 50 degrees. So I could have done it that way. I also know that if I kind of ignore the fact that this line is here, right, notice that what I have is an inscribed quadrilateral, right? I've got this four-sided figure whose vertices are all on the circle. And I know in a inscribed quadrilateral, the opposite angles are supplementary. Notice this is 90 and this is 90. They add up to 180. And I know that this and this have to add up to 180 as well. So I know that if this side over here is 80, this one has to add up to 100, making y equal to 50. So there was a couple different methods I could use here. Either way, they're all going to get me the correct answer. And then again, the last one we're going to do. Here we have, given that circle O equals circle P. So what they're saying when they're equal, they're basically saying that the radiuses are the same. So all of these values there are the same, whatever that is, right? We also know this is going to be a right triangle because, again, the side of this triangle is the diameter. So also the hypotenuse. So it continues to give us, it says arc AC equals arc AB. So arc AC, so I'm assuming this is A here. So AC equals AB. Well, remember, when the arcs are the same, their corresponding chords are equal. So we also know that these two lines are equal. So it says here, prove that triangle ABD is equal to triangle ACE. Well, we learned in a few chapters ago, I think it was the hypotenuse leg theorem, that if the hypotenuse and the leg of one triangle was congruent or equal to the hypotenuse and the leg of another triangle, then the two triangles were congruent. And so, yes, we know, being that we already know these two sides of the triangle, the hypotenuse and the leg equals the hypotenuse and the leg, we know that the two triangles are congruent. So again, I'm not going to ask you to do a proof, but if you were to do the proof, right, what we would need you to kind of know is you would have had to have proven that this chord here equals this chord here. That would have been the first thing. And the reason those chords are equal is because their arcs are equal. That was given. And then you would have to prove that these two lines are equal. Well, if the circle is the same size, their radiuses are the same, that meaning their diameters are the same. So that's how you would prove the sides. And then you would prove the triangles congruent using the HL theorem from a few chapters ago. And so that's how I would do that with a proof.